Hey guys, welcome back to another AP Chemistry video. Today we're talking about Unit 4. This is going to be about analytical techniques, so what we use in labs, for solutions, and we're going to talk about reactions as well. So it's split into two parts there for you. We're going to first talk about the techniques and solutions, then we'll talk about reactions. Okay, so some vocabulary. We'll talk about solutions, molarity, dilution, solubility, spectroscopy, the Beer-Lambert law, chromatography, distillation, net ionic equation, reduction, oxidation, titration, analyte, equivalence point, and indicator. Okay. So part one, we're going to talk about solutions and the analytical techniques here. Right? So for solutions, remember a solution is a homogeneous mixture that's formed when a solute is dissolved in a solvent. So the solute is what you're putting in. That's like the salt, the sugar, whatever you're putting in. The solvent is what is doing the dissolving. That's the water, the coffee, the tea, whatever it is. Okay. And these don't always have to be a solid and a liquid. It can also be two liquids. It could be different forms of matter. Okay. But solute is what you're putting in. It's what's getting dissolved. Solvent is what's doing the dissolving. You normally have more solvent. Okay. And we can measure the strength of the solution using molarity. Remember, molarity tells you how many particles you have in the solution. So the equation for this is moles per liter. Okay, so the number of moles of your solute, what you're putting in, divided by the liters of your whole solution. Right, so molarity is also something to talk about with concentration. So you can see here on the left, we have a low number of particles in the solution. On the right, we have a lot of particles. So the particles determine the concentration. So low concentration for the left, because we have less particles. That's the same thing as saying low molarity. Okay. The high concentration on the right is a high molarity solution. Okay. So does a high or lower molarity mean a stronger solution, and why? Here, a higher molarity is a stronger solution because we have more particles in there. We have more solute. Okay. The second one is if I have 6 liters container of water, so I have 6 liters of 6 liters of solvent, and I want to make a 3 molar solution, how many grams of NaOH should I add? Okay, so a little bit of math here, but what we're going to do is we're going to use that equation above. We're going to use the molarity equals moles divided by liters, right? So we had, let me zoom a little so I can write better. Molarity is moles divided by liters. Our molarity is 3. Moles is what you're looking for. And then liters is 6. Okay, so our moles is equal to 6 times 3. That's 18 moles. Okay, and remember to go from moles to grams, because what we're looking for is the grams of NaOH. We need to multiply by the molar mass. The molar mass you add up on the periodic table. If we add up sodium, oxygen, and hydrogen, we get 39.997. And if you multiply those together, we need to add 719.95 grams of NaOH to our 6 liter container of water. Okay. So make sure we know this equation for molarity. It will be very useful for you. This equation is on your formula sheet, so you don't have to memorize it, but it's a simple one to memorize. It's the moles divided by liters. Okay. So with solutions, we can have a dilution. Dilution, when it's more dilute, is you're making it less concentrated by adding more solvent, right? So an equation we have to determine how much solvent we need to add is M1V1 equals M2V2. The M's are molarities, V's are volumes. So M1 is your M1V1, that's your starting molarity at a certain volume. M2V2 is the molarity you want to reach at the final volume you need to have. So if we use this equation, the question says if I have a 5 molar solution at a 10 liter container, what volume of water needs to be added to make a 3 molar solution? Okay, so we have molarities, we have volumes, we'll use the equation. Our starting is 5 molar in a 10-liter solution, or a 10-liter container, and we want to end with a 3 molar solution. We want to find that second volume. So if we do the math, our V2 is 5 times 10 divided by the 3. So 5 times 10 is 50. Divided by 3, we get about 17 liters. Okay, so what volume needs to be added? It's our final minus the volume we started with. We need to add 7 liters of water. Okay, so the dilution, all you're doing is you're starting with a higher concentration and you add water to make it smaller. Right, you're adding water to make the concentration go down. And what to talk about here in a minute is a serial dilution. It's what's shown in this image here. We're going down by a factor of 10 each time. Okay, so we could more accurately display the information, display the molarities with something called absorbance, which we'll talk about here in a minute. All right. So solubility. We've talked about this before in the I forgot if it was unit 1 or unit 2 or unit 3, but like dissolves like, right? Like dissolves like means that similar polarities and intermolecular forces will dissolve with each other. So if something is soluble, it will dissolve. Insoluble will not dissolve. Okay. Miscible is when liquids will mix, and miscible liquids will not mix. So in this first image, this yellow solution, you can see, it's kind of hard to see, but down here, you can see a yellow powder forming. There's a powder in a liquid that's formed. That means it is not dissolving. That part is insoluble. Okay. The image on the right, you can see 3 liquids. They have distinct breaks and layers, right? So they're not mixing together. So this is immiscible. There's the same thing with oil and water, right? If you have like a pot of water, you normally see like drops of oil and things around it. That's because oil and the water are immiscible. Okay, so there's questions here. Of the following organic compounds, which is the least soluble of water? So remember, water is polar. So we want something that is not polar, does not have our hydrogen bonds. So in each of these compounds, we have an OH that has the hydrogen bonds. We have these oxygens here making the hydrogen bonds and making it polar. So the least is going to be C, hexane. And then the second question, I want you to go ahead and think about this and do it on your own. Which of the following substances has the greatest solubility in C5H12? So this one is non-polar. Okay, so see which one matches with that. Okay, so with solubility, the factors that affect the rate include the surface area. So how big your particles are if you have one big chunk, or if you break it down to like a powder, smaller pieces. Agitation, if you mix it together, it's going to have the particles collide with each other more. And then temperature, right? If you increase the temperature, the particles are moving faster, they have more energy, so they can collide with each other more often. The factors that affect the amount of solute that you can dissolve is the amount of solvent, right? If you have more water, you can dissolve more of your solute in there. The temperature. So with temperature, if you increase the temperature, you can dissolve more solids. But if you decrease it, you can dissolve more gases, right? So for gases, think about like a can of soda. If you put a can of soda in a fridge, it's typically fizzier. It has more bubbles than a can of soda at room temperature, right? That's because these gases at lower temperatures have less energy, they're moving slower, so they can't escape the liquid as easily. So the gas stays inside the liquid, makes it fizzier. Okay, and then pressure for gases only, right? The pressure increases as if you increase pressure, the solubility of gases also increases. Okay, and one thing I want to point out is, remember, we have these reaction diagrams. We've seen these before, right? You have a certain amount of energy, the activation energy to get the reaction started. That's why things like temperature are important, because it increases the amount of energy you have. Okay. So with solubility with temperature, it affects the saturation of solutions. Remember, saturation, we're talking about how much can fit in there. So a saturated solution contains a maximum amount of solute for a given solvent, right? So if I have a beaker and I put something in here and everything dissolves, but if I put a little bit more and I start to see them on the bottom, that means I've gone over. So before I put a little bit more, it's saturated. It has the most that I can hold. Unsaturated means that if I put some in there, if I put some solute into here, it's going to fully dissolve. And if I put more, it's going to keep dissolving because it's not saturated. It can still hold more. Supersaturated has more than what it can hold at room temperature, right? But supersaturated, you need to increase the temperature. You heat it up and let it dissolve. Then you're going to let it cool down and it's going to be supersaturated. A thing with supersaturated is if you add some agitation, if you add some crystals into there, it'll recrystallize the solute and it'll come out of solution, right? So with these images, unsaturated means you can put some in there and it'll keep dissolving. Saturated means if you put some in, you'll start to get that at the bottom because it's already done dissolving. It's not going to add more in there. Supersaturated, you heat it up. So we added some heat and everything dissolves. But if we add some agitation and put a little crystal in there, you get some solid out. Okay. So let's look at this chart here and talk about each of these solutions, either unsaturated, saturated, or supersaturated. Okay, and we're talking about the original solution, not after adding. Okay, so for solution 1, all of these are in 100 milliliters of water, and we're adding some NaCl. Solution 1, we added 30 grams of NaCl, and after 5 minutes, nothing is left over. All right, everything dissolved. That means our original solution was unsaturated. We can add more into it. Solution 2, we added 30 grams, and we had 45 grams at the bottom. So we gained some. It increased, right? 30 grams to 45 grams, we increased. So the original was supersaturated. We added some crystals and some more came out from the solution. Solution 3, if we add 30 grams and 30 grams stays on the bottom, that means nothing dissolved. We were already saturated. We already had the max that we can hold, so nothing more can dissolve. And in solution 4, we added 30 grams and only 10 grams is at the bottom. That means originally some more could dissolve, but not all of it. So this started as unsaturated and it became saturated. Okay. All right, so with solubility, knowing if something dissolves or not, we have charts like this sometimes. This is one that we saw for on-level chemistry and advanced chemistry. I'm not sure about the chart used for on-ramps. But you can use this kind of chart to determine if something is soluble in water or not insoluble. Remember, soluble means it can dissolve. Insoluble means it cannot dissolve, right? So the word precipitate means that if you mix two things together, it forms a solid, right? Like that yellow solution we saw earlier, it formed a yellow powder. That was a precipitate. You mix liquids together and it forms a solid. Okay. These solubility rules here are what you need to know for AP, right? So your group 1 salts, so Na, lithium, potassium, rubidium, all those group 1 salts are soluble in water. It will dissolve in water. Anything with ammonium, NH4, is soluble. It will dissolve. Anything with nitrate, NO3, will also dissolve. It is soluble. And then your halogens, so Cl, Br, and I, are soluble unless they're with these three here. If they're with silver, lead, or mercury, they're insoluble. They will not dissolve. But with anything else, they will dissolve. Okay, that's just some general rules. There are some exceptions, but for AP, you can follow these rules here. Okay. And then solubility graphs. Okay, again, this is something you talked about in 10th grade. Remember, we have these graphs that show solubility for different compounds based on the x-axis we have temperature. On the y-axis, we have our grams of solute, so in 100 grams of water. And if you're on the line, it is a saturated solution. Below the line is unsaturated, above is supersaturated. Okay, and remember the lines is for a specific compound. So this one here is for NaNO3, If we are on this line here, it is a saturated solution. If we are above, it is supersaturated. Below is unsaturated. Okay. And remember, as solids increase the temperature, it increases solubility. For gases, it decreases. That's why NH3 is going down there. Okay. So first question here, why does solubility of gases decrease? Remember, we talked about how lower the temperature, the slower the gas particles move, so they're able to stay in the solution. If you increase the temperature, the gas particles are moving faster, so they can escape and leave solution. Okay. And then the second question is, how many grams of KClO3 are required to saturate 550 milliliters of water at 4 degrees Celsius? Okay, so we're going to start. We have KClO3, 4 degrees Celsius. So at 40, right, we're at about here. This is, let's say 15 grams. That was a bad line. About 15 grams. But remember, this is in 100 grams of water per y-axis. So 115 grams per 100 grams of H2O. If we want 550 milliliters, remember, water has a density of 1 gram per milliliter. So 550 milliliters is equal to 550 grams. Okay, so from 100 grams to 550, that's about a 5.5 times increase. So we're going to do 15 grams that we originally had times the 5.5 increase, and we should get 825 grams of KClO3. Okay, so that's how you're going to use these kind of graphs here. Okay, so going into our analytical techniques now. Spectroscopy is a process that uses light to determine the shape and composition of substances based on how they interact with light. Okay, if you were in on-ramps, you used the colorimeters with blue 1 dye to do this lab. We're going to do a lab similar this year in AP as well. Okay, so remember, we've talked about different waves of light. Microwaves create the rotational changes. Infrared is vibrational, and an ultraviolet and visible, this is what we care about here. This changes the energy levels for electrons. Okay, so using visible light, we can talk about the molarity based on Beer's-Lambert law. Beer's-Lambert law is this equation here. This is on your reference sheet. A is going to be the absorbance, that's what we measure. The epsilon is your molar absorptivity coefficient, that's a constant for the compound. C is the concentration. And then L is the optical path length. That's normally 1 centimeter, but it could be different. Okay, so if we have known concentrations, we can determine the absorbance for an unknown. Okay, the way we do this is, remember, a spectrophotometer. You're using a given molarity, you know your molarity, and you're determining the absorbance. Right, you can do this for a set of data. You can get multiple different molarities that you know, and you can graph them to form a relationship. Okay, remember when I talked about how we had the different containers, the dilutions, where it started off with 100, molarity of 100, molarity of 10, 1, and so on and so forth, right? It got smaller and smaller. That was called the serial dilution here. So we can use a serial dilution to make this graph, and that makes a calibration curve. We get an equation of y equals mx plus b from this line, and that relates back to Beer-Lambert law. So your y is your absorbance, your x is your concentration, and then your m is the other factors, the path length and the molar absorptivity. So if the m stays the same, it stays constant. If you have a calibration curve like this, you can put in an absorbance of an unknown. So you can put some unknown solution into the cuvette, put in the spectrophotometer, determine the absorbance, and then plug that into this equation to figure out your concentration. Okay, so that's something we're going to do with a lab. You'll see that more there, and we'll have some questions with this as well. Okay. Chromatography, again, on-ramps did this. Advanced didn't do this as much. I don't know if you did it at all, but on-ramps definitely did do this. Okay, so what chromatography is a technique to separate a mixture based on polarities. Okay, so we're gonna use different solvents. Essentially what happens is you have this plate here, a silica plate, and you're gonna put your sample here on the bottom. That's what the dot is. Okay, that sample, you're gonna put it into a beaker with a solvent, and a little note for this: that sample, the dot, should be above the water line. It should not be inside the water line. That's just the best picture I can find right now. Okay, so the dot should be above the water line, and you're just gonna put, or not water, the solvent line. It doesn't have to be water. And what's gonna happen is that solvent is gonna climb up the paper, and as it does, it's gonna take the compounds up with it, right? So whatever we started with here, it was made of 3 different things. So we can separate based on polarities, okay? And that upward movement of the water, that's called capillary action. All right, so what we can use this for is based on our solvent, we can determine what our compound is made of. So a polar solvent, like acetone, will carry polar compounds up. So if, for this example down here, we had a polar solvent, then our blue dot up here, compound A, would be the most polar. Compound C would be the least polar. Because if a polar solvent is going up, the polar compounds are going to go up with it. If it's a non-polar solvent like hexane, then it would be the opposite. If hexane was going up, it's non-polar, then the one that went up the furthest would also be the most non-polar. The one that went up the least would be the least non-polar, or the most polar. Okay. Sometimes you'll have to figure out what kind of solvent it is based on the media. Okay, or you'll just use the media instead of, so the plate might be polar. So if the plate is polar, then what goes up will be the most polar. If the plate is non-polar, what goes up would be the most non-polar. Okay, so it's all just based on polarities. So this with the plate is thin layer chromatography. You can also have column chromatography. It's the exact same thing, just inverted in a column. So you have essentially just what's covering the plate inside of a column. You put your sample on top, and then you're gonna run your solvent down into it. And that solvent is gonna separate the solutions into what we call bands. That band is the different compounds. Okay. All right, and with chromatography, with the thin layer chromatography, so with this paper version, you can measure the distance that the compound moved versus the distance from that the solvent moved, and use what we call the RF factor. The RF factor it's a ratio of how far it moved. So it's the distance that was moved by the compound divided by the distance of the solvent. Just tells you how far it moved up the paper. All right, and then the last technique we're going to talk about is distillation. Distillation separates a mixture of liquids based on their boiling point. So as chromatography, we separated a mixture based on polarities. Distillation, we're separating a mixture based on boiling points. Okay, so what happens is we have a flask here on the left with our mixture. We're going to heat it up slowly. And as we heat it up slowly, our liquid's gonna boil. Okay, so our boiling liquid's gonna go up. It's gonna go up and into this tube. This tube is called a condenser. So it has water line. That's what these 2 tubes here are. The water is running through the center. It does not make contact with the gas. But what it's going to do is it's going to cool the gas down. So the gas is going to condense back into a liquid and go down into this container, this flask here. Okay. So compounds have different boiling points. So if you know your different boiling points, you know what temperature to go to, and you can boil them out one by one to separate them. All right. So our second part, we're going to be talking about reactions. Okay, so we'll talk about some different types of reactions, and then we'll talk about equations, writing the equations. All right, so types of reactions, you've already seen these before. We'll have 6 main types of reactions. We have synthesis, where you're taking two things and they combine to make one. Decomposition is opposite. It's one thing breaking down to two or more. A single replacement is when you have one thing, the zinc here, is replacing something in a compound. So the zinc comes in to replace the silver, and the silver gets kicked out. All right. A double replacement on the top right is when your two metals, so your Na and Ca, are going to switch places. Okay. Combustion is when you have some hydrocarbons, so something with carbon or hydrogens. It reacts with oxygen to make water and carbon dioxide. Remember, for combustion, these parts here, the oxygen making water and carbon dioxide, that stays the same. The only thing that will change is the hydrocarbon. And then the neutralization reaction is when you have an acid plus a base react to make water and a salt. Okay, so an acid-base reaction. So those are 6 types of reactions. With these, you should be able to write a balanced equation. Okay, so for example, hydrogen gas reacting with oxygen gas. We have H2 gas plus O2 gas. And if these react, we can make water, H2O. Okay, this isn't balanced. We need to make sure it's balanced. So H2O, this could either be liquid or gas depending on temperature. We're not certain. But H2O has 1 oxygen. Here we have 2 oxygens, so we need a 2 on the right side. That makes 4 hydrogens. We have 2 hydrogens on the left, so we need a 2 on the left side as well. Okay, I want you guys to try doing these other 2. Write these out. And make sure you balance the equations and have the symbols. Have if it's a gas, liquid, or solid. Okay. And then we're going to talk about ionic equations. All right, so ionic equations are different ways to write a chemical reaction. So we have a chemical equation. That's what we just did. It shows everything that's happening in the reaction. An ionic equation takes everything that's happening and it breaks it down into ions. If it's a solid, it does not break down because it's a solid. It's not going to dissolve. But everything else breaks down into ions. Okay, so what this looks like is here, right? The complete reaction. That's just all the compounds, how they are. The ionic equation takes everything except for the solid stays together, but everything else breaks down to its ion components. So sodium becomes a sodium plus 1. We had a 2 as a subscript for the sodium, so we have 2 of those ions down here. Okay. The third type, the net ionic equation. Net means that you're balancing it out on both sides, or you're eliminating what's the same. So you can see here, there are some red slashes for what's canceling out. We have 2 sodiums on the left and 2 sodiums on the right, so we cancel those out. Everything that's remaining is what we leave. Okay, and then half reactions we'll talk about later. Half reactions shows just for one species. So we can show the reaction just for barium or just for the carbonate, right? Not both of them together. Okay, so let's do some practice with this. So write the complete and net ionic equations for the following. Okay, so for the first one here, we have nickel nitrate plus 2 potassium bromides make potassium nitrate and nickel bromide. Okay, so the first thing we need to do is determine if things are liquids or solids or what's happening, right? So these ones here are both going to be aqueous. Remember, aqueous means that it's dissolved in water. And we know this based on our solubility rules. Okay, so if we separate these into the complete ionic equation is already written here. But if we separate these into ions for our ionic equation, it's going to be nickel. We have 2 nitrates. So remember, nitrate's a -1, so we know this has to be +2. So nickel +2 plus 2 of our nitrate ions plus 2 of our potassium ions plus 2 of our bromide ions goes to, we have 2 potassium ions 2 nitrate ions. We have our nickel ion. And we have 2 of our bromide ions. Okay, so that's our complete ionic equations, what was given to us. Net ionic, just our ionic equation is what we wrote down here. There is no net ionic equation because everything cancels out, so that one will not have the net. It's just an ionic equation. Okay. For the second one, aluminum phosphate is going to be our solid here. And then KNO3 is going to be aqueous, it's going to dissolve. So that's our complete ionic equation. Our net, we have 3 potassiums plus our phosphate. We have 1 aluminum, 3 nitrates, and that goes to 3 potassiums, 3 nitrates, and then our aluminum phosphate here is going to stay together. Okay, so what cancels out is our 3 potassiums, not 3 nitrates. So what we have left is our phosphate plus aluminum make aluminum phosphate. So that is our net ionic equation. All right, I want you to do the same thing with this example down here. Figure out which one of these is going to be a solid first. One of them is going to be solid. The other one will be aqueous. Then write the net ionic equation. Okay. All right, in the last part of our notes, I believe, second to last part of the notes, is going to be redox. Redox stands for reduction and oxidation, right? The red from reduction, ox from oxidation. And this talks about the oxidation state of a compound or an atom. The oxidation state is a fancy way to say the charge, the positive, negative, or neutral charge. Okay, so elements have a charge of 0, an oxidation state of 0, right? So if I just have aluminum metal, has a charge of 0. Hydrogen gas has a charge of 0. Okay, remember diatomics here will have a charge of 0 as well. Okay, for reduction, this is when elements gain electrons. So when you gain electrons, remember electrons are negative, it's going to decrease the oxidation number, make it more negative. Oxidation loses electrons. So if you're losing the negatives, it's going to increase the charge. Okay, so the charges you need to know, right, aside from what we already had on the periodic table with the groups, right, the +1, +2, etc. So group 1 is +1, group 2 is +2. These ones we talked about already. Your halogens are -1. We've talked about that. Oxygen is normally -2. The exception is peroxides. So if you have something like H2O2, it's a -1 charge. If it's an F2O, it's a +2 charge. That's not very common, though. I wouldn't really worry about that. But the peroxide is a -1 charge. For chlorine, the halogen is a -1 normally. But if it's in compounds with oxygen and fluorine, you should figure out the charge instead. Okay. Hydrogen is +1. But if it's with a metal, like NaH, sodium hydride, it has a -1 charge. Okay. Either way, whenever you're figuring out the oxidation state, remember that oxidation states from a neutral compound should be 0. If it's for a polyatomic, the polyatomic ion has a charge. You can figure it out there. Okay. So you will be given compounds like this in some of your practice, and you'll have to figure out the charge for each part of it. Okay. So let's do one of these together. Let's do NaNO3. We're just looking for the charges for each of these. So Na, N, and then O. What I like to do is I start with the middle first. Start with what comes in front. We know sodium has a +1 charge. Then go to the very back. Okay, so we know nitrate has a -1 charge. Our 3 oxygens with a -2 each is -6 charge. Okay, now we need our nitrogen here to balance it out. Okay, so we have -6 from the oxygen and a -1 from nitrate. So -6 here, the -1 here. we need to make sure we reach the -1. So this needs to be a +5. Okay. That way, if we add up all of these, right, because we didn't have a charge on the compound, this does go to 0. Right. I want you guys to try the rest of these. Figure out the charges for each part of it. Okay. And when we're talking about oxidation or reduction, so down here, we're figuring out which elements were oxidized and which were reduced. So remember, oxidation means that it lost electrons. Reduction is gain. Okay, so way to remember this. I skipped it, sorry. Right here. Oxidation is loss, oil rig, and reduction is gain. So what I mean by loss is loss of electrons. So oxidation, you were losing electrons. Reduction, you were gaining. A way to remember it is oil rig. Okay. So let's look at this example here. To determine to determine oxidation and reduction, we need to know the charges first. So for HBr, we know Br is -1, H is +1. Cl2, it's a diatomic element, so it has a charge of 0. Br2 is a diatomic element that has a charge of 0. Then H is +1, Cl is -1. Okay. So what's changing is our Br goes from -1 to 0. Our Cl goes from 0 to -1. Okay. So our bromine, if it's becoming more positive, it's losing electrons. That means it's oxidation. For chlorine, if it's becoming more negative, it's gaining electrons. That means it's reduction. Okay, so that's how you determine if things are oxidized or reduced. I want you guys to work through the rest of these, figure out which elements are oxidized and which ones are reduced there. Okay. There's one that you will have nothing is oxidized or reduced. So be careful with that, okay? But the other two, there will be something oxidized and something reduced. Okay. So with redox reactions, remember we talked about half reactions. We'll talk about here in a minute. This is when we're going to talk about it. Half reactions, we are only looking at one species at a time, right? So if we have this reaction here, we have aluminum plus we have HCl split apart into the ions, make the aluminum H2 gas with the chloride ions. Okay, so we can split this into two pieces, the half reactions. Okay, half reactions, we're looking at one element. So here we're only looking at aluminum, but we're looking at it with the electrons. So aluminum goes from being a solid to a 3+ charge. That means we gained 3 electrons, we lost 3 electrons. It gave off 3 electrons. So if it gives off electrons, that makes it a product there. Okay. For hydrogen, it went from a +1 charge to a 0 charge. Okay. So if we gained electrons, that goes as a reactant. Okay. So from this net ionic equation, we can bounce out the electrons. So to bounce out the half reactions, after we get our 2 half reactions, on the left side, we have 2 electrons. Right side, we have 3 electrons. So to bounce it out, we need to multiply the top one by 2, the bottom one by 3. Okay, that's what's happening in this step here. And that's just to bounce out the electrons. That way the electrons can get canceled out. And then you'd have your net ionic equation there. Okay. So write the half reactions for the following. So write our net ionic equation first. We have 2H plus 2Br minus plus Cl2 goes to 2H plus 2Cl minus plus 2Br2. Okay, so this is our equation. So there actually should not be a 2 there. That should just be Br2. Okay, so that's our equation. So what is changing? The H plus stays the same. We can cancel that out. Okay, our 2 things that are changing are the Br. So we can do 2Br minus goes to Br2. Okay, and if that's going from -1 charge to a 0 charge, that means we're losing the 2 electrons. Okay. Then we also have the Cl2 goes to 2Cl minus. So Cl2 goes to 2Cl minus. And if we're gaining electrons there, that means it's as a reactant. So those are 2 half reactions. Okay, so the half reactions are only for the parts that don't cancel out. Okay. So some vocabulary words, the parts that don't cancel out, the Cl and the Br, those are participating ions because they're participating in the reaction, they're actually doing things. The H plus is getting canceled out, that's our spectator. Because the spectator is just watching, it's not actually actively participating in the reaction. Right? I want you all to try to do the half reactions for those 2. All right, and then the last part we're going to talk about is the neutralization reaction. We're not going to do a lot here, just introduce it, introduce titrations. This is something we're going to do in Unit 8 with our acids and bases. Okay, but what a titration is a volumetric analysis. So volumetric means we're actually using volumes. And we're using a known concentration of a titrant to determine the unknown concentration of an analyte. So we're using the known concentration of one thing to determine the concentration of something else. And this can be used with acid-base reactions. Like I said, we'll talk about that with Unit 8. It can also be done with redox reactions. Okay, so you can do a titration with a redox reaction to determine the concentration of something. Okay, so some vocabulary with this. The titrant is the solution that you know the concentration of. This goes inside of your burette. That's that long cylinder on top. Okay. The analyte is your unknown. That goes in your flask. The equivalence point or the end point, that's when your stoichiometric molar ratio is reached, and that will be when you see a color change normally. Okay. So an indicator is something that's put into the solution, into this flask down here, to change colors at the equivalence point. Okay, so if you were in advanced chemistry, you did a titration for acid bases. You used phenolphthalein that turned pink, right? It went from clear to pink. That is an indicator. All right, and then with neutralization reactions, you'll see a graph like this when you do it. So if let's look at this left side first. Okay, so the base is in the burette. So that means our blue here is our base. Our red is our acid. Okay, so as the reaction happens, an acid has a low pH. You start low because it's looking at pH and volume of base. As you add your base, it's going to start becoming more basic, and then it's going to shoot up. The shooting up, the center of that is going to be your equivalence point. The equivalence point, the molar ratio is equal. So moles of our base is equal to moles of our analyte. That's when the color change happens. That's when the phenolphthalein goes from clear to pink. Okay. And then after that, it just plateaus off as you add more base because there's no more acid left. Okay. And then the other term that we need is the half equivalence point to read these graphs. So the half equivalence point is what it sounds like. It's half of the equivalence point. So if our equivalence point S was right here at about, let's say 14 milliliters, the half equivalence point is literally half of it. That's going to be at 7. All right. So that's all we're going to talk about with neutralization and titrations for this unit, just to introduce it. We'll actually do one of these and talk a lot more about reading the graphs in Unit 8. All right. But we will get there eventually. That'll be semester 2. I will see you guys next unit for Unit 5. If you have any questions about any of this, remember, make sure you're asking in class, ask during tutoring, get the help you need. All right? Have a good day.